This whole chapter is all on electrons. Why are electrons so important? Well, this is an image of the Hindenburg, which was a balloon, a hot air balloon in 1937. And a bunch of people died on it because there was hydrogen that leaked. And hydrogen is super reactive and very, very flammable. So we don't fill balloons with hydrogen, we fill them with helium. Even though they're neighbors on the periodic chart, they're really close to each other. They're in separate columns. Hydrogen is super reactive. Helium, on the other hand, which is a much better choice for balloons, has a stable configuration. And that stable configuration is really coming from its electron configuration. It has 2 electrons in its outermost shell. And when you're tiny like that, that makes it especially stable. So what about helium makes it inert? It's that it has this stability in its outer electron shell. By contrast, why is hydrogen so reactive? Because it has an extra electron, has 1 electron in its outermost shell. It doesn't have a complete set. It wants to get rid of that electron. This is also why hydrogen tends to react with itself to form a diatomic molecule. And there are other atoms out there that are as reactive as hydrogen is. Mainly the things in column 1 are also reactive in that way. So we talked about the organization of the periodic chart, right, and how Mendeleev set it up where elements within a compound have similar properties. Particularly, they like to give up or take electrons in a specific way to give us a predictable ion charge. We're going to talk about now why that is the case and what the electrons are actually doing and where they live. So when talking about electrons, we have 2 different models that we use. The first one is the Bohr model. That's the really simple model of electrons. That's probably, if you've taken chemistry in high school or done any really basic chemistry in a different science class, that's probably what you used. That's like the solar system model. So the nucleus is in the center and the electrons rotate around on these little tracks. We have a more advanced model called the quantum mechanical model that helps to explain everything the Bohr model can explain plus more. Both of the models are useful. The Bohr model is useful in that it's so simple. It's easier to teach people who don't know a lot about chemistry, the positioning of electrons, but the quantum mechanical model just has more predictability power. So we'll look at both of them. So here's a picture of Bohr and Schrodinger. These are 2 guys, along with Albert Einstein, that developed quantum mechanics, which was this really revolutionary concept idea that stretches not only into physics, but also into chemistry. And they have this whole idea that goes with wave particle duality of an electron, or that electrons and small particles like photons of light have properties of waves, and they also have properties of particles. So it's not that they just act like one or the other, they actually have a combined properties of both. And it gets much more complicated than that, but we're not going to talk too much about that. What I do want you to no, I guess we'll backtrack for a second and then talk about the electromagnetic spectrum and electromagnetic radiation. So light, like the light that's bouncing off of, your computer screen and your eye is picking it up, light coming from the sun, light coming from all sorts of different sources, is a type of electromagnetic radiation. Light is specifically a type of energy that travels at the speed of light. 3.0 times 10 to the 8th meters per second, fastest speed in the universe. Light has properties of both waves and particles, just like electrons have this wave-particle duality. So some properties of light are going to behave like a wave, some are going to behave like a particle. Are there other types of electromagnetic radiation outside of just light? Yes, there's electromagnetic radiation that is higher energy than natural light, and there's electromagnetic radiation that's lower energy. So we can sort of think of electromagnetic radiation in terms of being a wave. When you have water and you disturb it. So here we've got a little droplet that's fallen down. It creates this wave, and that wave brings energy with it. So if you were like a little mosquito hanging out on the surface of this water, you would feel that energy, right? Or when you're in the ocean, you feel the energy of that wave. So light carries a certain amount of energy, and that energy is related to its wavelength. When I talk about wavelength, it's the difference between crest and crest or trough and trough. Okay, not crest to trough. Crest to adjacent trough would be half of the wavelength. The symbol we use is this little cursive L thingy that's called a lambda. And wavelengths change. So depending on what radiation you're looking at. So higher radiation, higher energy radiation has a really short wavelength. Lower energy has a really long wavelength. So that happens even within natural light. When we have the colors of the rainbow, red light is a much longer wavelength than violet light. Specifically, if I was to take natural light, like from the sun or from an incandescent light bulb, not neon lights, but incandescent lights, and we run it through a prism, we split the light up because natural light has all the colors in it, right? That's what a rainbow is. When you see the rainbow, it's the natural light coming from the sun. It's being refracted through the water droplets in a cloud, and you get to see all the quote unquote hidden colors that are within that natural light. Natural light has all the colors. That's why when we're standing under natural light, we can see all the colors around us. When you're standing under a black light, it's missing some of the colors in the spectrum. That's why you don't see all the colors like on your shirt and things like that. Certain colors will disappear, or quote unquote disappear. It's because the color isn't preserved in the light source. But under natural light, we have the full spectrum. The longest wavelength is going to be red light, which is 750 nanometers. You don't need to know like the exact nanometers or anything like that, but you do want to know their relative ordering. So longer red light, shorter violet light. Violet light is at about 400 nanometers. They're within the same magnitude, right? 750, 400, within the same magnitude. They're not that far away from each other. This is a very small distance. A nanometer is 1 × 10 to the -9. So yeah, Roy G. Biv, if we were to take a light source and run it through a prism that splits the light open, we would see all the colors. Red being the longest wavelength, violet being the shortest. Well, this is sort of a random. I feel like the first part of this is kind of random. Here's a random slide. So when you see a red shirt, what you're actually seeing, like we look at this woman's shirt and it's red, what you're actually seeing is the red light reflecting off of her shirt. So the chemical composition of her shirt is absorbing every color in the light spectrum except for red. So it's almost like the innateness of the shirt is actually everything but red, right? The red is reflecting off of it and bouncing into your eye. So her shirt, because of the chemical composition, is absorbing orange, yellow, green, blue, and purple, and it's saying, I don't want red. And the red is what's reflecting back, and then your eye's picking that up. If you looked at like something that was green, it is absorbing all the colors and reflecting green back at you. So our eyes are really only seeing the reflected light. All the rest of it's being absorbed. So in relationship to like wave properties, we have the wavelength, and then we also have this thing called frequency, which is sometimes this little cursive V shape, and this is pronounced nu, N-O-O. It's defined as the number of cycles or crests that pass through a stationary point at a given second. So it's like, how quickly are those crests coming? Are you in a wave pool and the waves are coming really slow? You know, every 2 seconds, 3 seconds, or is it fast and you're getting like 3 waves per second? Okay, you're going up, 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 up. That's the reference, that's the frequency. Frequency is always going to be inversely related to your wavelength. So if you have a really long wavelength, it's going to take a long time for you to get from crest to crest. If you have a short wavelength, you're going to go past those crests really fast. So your frequency will be inversely related. Inversely related means as one goes up, the other goes down. We can also, like some of the properties of light are also similar in thinking of them as a particle as opposed to a wave. So a particle of light is known as a photon. We can think of it as like a packet of light energy. And the amount of energy that that packet carries is really dependent on the wavelength of the light. So if your packet has a wavelength that is 750 nanometers, that photon will be red light. If it has a wavelength of 400 nanometers, it'll be violet light. If it's something smaller than 400 nanometers, it becomes a higher energy electromagnetic radiation. So light waves carry more energy if their crests are closer together. So that is another concept that you kind of want to layer on top of wavelength frequency, is that energy is higher when your frequency is higher, or energy is higher, more energy when your wavelength is shorter, because you're getting hit with more waves faster. The violet light has a shorter wavelength, which means it carries more energy per photon than red light. If you've ever taken yoga or done Eastern philosophy stuff, and they talk about the chakras and the rainbow, and bathe yourself in red light if you want to feel grounded, and bathe yourself in violet light if you need energy, right? Part of that idea, I think, is coming from this place of violet has a shorter wavelength, so it has a higher energy. Yeah, the energy between those two is not going to be great enough, I don't think, for you to feel it. If you want higher energy, you can go sit under some gamma radiation. That'll liven you up. So are there other types of electromagnetic radiation? Yes, and you want to know these or know the ordering of them. So our natural light sits right here, and we said that was roughly in the nanometer section. If we go on the outside of red light, so let's say our wavelength is just a little bit longer than red light, our eyes can no longer perceive it. Okay, our eyes can only perceive in this window. Once we get outside of this, we move into what's known as infrared radiation. Your body gives off heat. Infrared radiation can pick that heat up. Some animals can actually see in infrared radiation. We just aren't one of them. So longer wavelength there. As we move in this direction, as we increase the wavelength, as the wavelength gets longer, the frequency gets shorter and the energy gets lower too. Okay, so these are lower energy things. If we are even longer than infrared radiation, we move into what's called a microwave. And these are, in fact, the microwaves that you find in your microwave. People are always like, oh, don't stand in front of the microwave while it's running. No, microwaves are harmless, okay? They're not going to do anything to you. They're super long. They're fine. How does a microwave work? I mean, you don't want to be inside a microwave oven, but you can stand in front of the microwave. You're going to be fine. How a microwave works, it's kind of cool. The wavelength of a microwave is just long enough that when it passes through a material, if it hits a water molecule, it'll spin the water molecule. And when you spin all the water molecules in something, you create friction, which creates heat. So how you're heating your food in the microwave is you're passing these electromagnetic radiation waves through it, and it's pinging all the water molecules, making them all spin, and then heating your food up. So if you put something in the microwave that doesn't have water or moisture to it, you can't heat it up. Doesn't work. Also, if you have something like I have this one clay cup that I always put in my microwave. I don't know why I do, but the cup ends up getting hotter than the water does, I feel like sometimes, because the cup is holding on. The clay has a high water retention, and so it's heating the water up in that. If we go longer than microwaves, we move into radio waves, which are the longest and the lowest energy. Those travel through space. We use them for TV. We use them for radio. We use them for cell phone towers and things like that. If we go into higher energy, okay, these things, like I was saying, is harmless. As we move in this direction, we are shortening our wavelength. We're increasing the energy of this electromagnetic radiation. So these we want to take in smaller doses. If we go just outside of the violet light, we move into ultraviolet radiation or UV rays. Again, there are some animals that can see in UV rays. I think the mantis shrimp can see in the spectrum from infrared to UV radiation. He has a lot more cones in his eyes. But that is the stuff that comes off the sun, right? It's what filters through the atmosphere and gives you a suntan. It can also give you a sunburn. And if you interact with it too much, it can give you skin cancer because it has higher energy than kind of what our safe zone is. If we move past ultraviolet radiation, we move into X-rays. Those have an even shorter wavelength. If you've ever gotten an X-ray, the person who's providing you with the X-ray goes and stands behind a concrete wall because they don't want to experience X-rays on a regular basis. A couple of them in your lifetime, not a big deal, but you don't want to be getting X-rays all the time. And X-rays are especially, or your like sexual organs are especially sensitive to X-rays. So usually they give you like a big lead pad that you put over your special areas because you don't want X-rays going into, whatever your cells are there. The highest energy is going to be gamma rays. Very, very high energy. These come off the stars. Okay. Our sun produces a lot of gamma rays, but we have this thing outside. It's even bigger than our atmosphere. So we have our atmosphere, and then around that we have this thing called a magnetosphere, and it is produced from the rotation of the molten lava within the core of our Earth. That magnetosphere, I know that sounds like something out of like X-Men, but it is a real deal thing. That protects us from gamma radiation. So we're not getting fried constantly by gamma rays in space. Okay, we'll go play with something else in teaching. Sorry. So gamma rays, high energy. Also, gamma rays come off of like nuclear waste, power plants, anytime materials decay radioactively. So it's not stuff you want to be around. Gamma rays can be so high energy that they can actually and the wavelength is so small and the energy is so high, it can cut through your DNA in your cells. So it's nasty stuff. So know the ordering of those. This kind of talks about what we already said, blah, 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 blah. Okay, but I do want us to look at this. So we've got three different things here. We've got visible light, which is natural light, X-rays, and microwaves. I want you to put these in increasing order of wavelength, of frequency, and then of energy of a photon. So go ahead and do that. I'll give you just like a minute and a half for that. You don't have to do it for everyone, but do it for visible light, X-rays, and microwaves. Okay, so if we are arranging these in order of increasing, that means we need to start with the smallest. So the smallest wavelength of these three is going to be our X-ray. If we go back to our chart over here, we can see X-rays has the smallest wavelength. Then we go to visible light, then we go to microwaves. Okay. If you can organize that, then the other ones come kind of easy because it's an inverse. So we just flip them, right? If this first one is going to be microwave, no, going to be X-ray, and then visible light, and then microwave is the longest. We know that frequency is going to be inversely related. So it'll go micro, then visible, then X-ray, right? And then these two things, this one and this one, are directly related to each other. So it will follow parallel to micro, visible light, and then X-ray. Or microwave has the lowest energy, visible light has actually a higher amount of energy than microwave, and then X-ray has the highest amount. So inversely related. Okay, so why are we talking about light when we're supposed to be talking about electrons? Well, because having a basic understanding of light and its energy helps us to understand the electron models that we're going to use. So every element that's on the periodic chart has its own unique, what's called an emission spectrum of light, or it produces a certain type of light. So neon produces this sort of red color to it. If you've heard of a neon sign, the tubes that are red are really the ones that are neon. The other tubes are different materials. So for instance, mercury lamps or mercury placed in a vacuum will give you a blue color, hydrogen will give you a pink color. And this is consistent across the board. So if you're lighting up a bunch of hydrogen, it doesn't matter if you're here or you're in, Brazil or you're on the other side of the universe, it's always going to produce this similar color. How do we, quote unquote, light or excite these materials? One way is to plug them into an electric current, like a lamp. Another way is to put them into a flame to do what's called a flame test. So you take a liquid amount of this material and you put it in a Bunsen burner and it will burn a very consistent color, depending on what it is. So you can use these different colors and also their spectrum. And the spectrum is just when we take the light and we spread it out through a prism. We can use them to identify what the material is, match colors. So here are some of the spectrums. Now a spectra, remember, is when we take whatever light we're seeing and we pass it through a prism to see what it's made up of. So white light will produce this, right? So we will have all the colors of the rainbow. Let's say we have a lamp with hydrogen in it. Well, hydrogen light only has this sort of orangish color, a blue, kind of a bluish purple, and then a violet over here. So if you had a green shirt and you were standing underneath a hydrogen light, your green shirt wouldn't look green because that isn't in the present light to reflect off of your shirt. Helium has a couple more lines. Neon has quite a few. So if you stand underneath neon light, usually you'll see most of the colors. But you don't have as much of a spread as you would in natural light. Again, these are signatures. These are unique to each element. So every single element has its own unique spectrum. So here's our hydrogen. Hydrogen is the simplest one. Think where hydrogen is on your periodic chart. It's number one proton, one electron. Okay, so there's not a lot of creativity with what the electrons can do. There's only one electron. These are the colors that we're going to get. Now, why do we get these colors at specific points? Well, Bohr developed a really simple model to explain what was happening. So he came up with this quote unquote solar system model, or this model of orbits for electrons. And it is important that you know it's orbits, orbits, because the quantum mechanical model has something called orbitals with an AL, and they mean something different. So in the Bohr model, we have our nucleus in the center that has our protons and our neutrons in it. And then the electrons will ride around on tracks outside of nucleus. These tracks are very nice and clean and even and consistent. The track closest to the nucleus is given a number value. It's called n equals 1. The second closest is n equals 2, and you move all the way out. The quote unquote lowest energy, or the easiest thing to fill, or the first electron orbit to fill, is always the first one. Okay, so in general, if the electron is in ground state, it's not excited, it's going to move as close to the nucleus as it can. Why? Well, the nucleus has got protons in it. That positive charge pulls on the electrons. So the electrons will naturally fall closest to the nucleus. If I excite this thing, like plug it into a wall, right? Or put it in a flame, this electron will absorb energy. And what that electron will do is it will start to jump to higher energy orbitals. Depending on how much energy this atom receives, that electron can jump from the 1 to the 2 or the 1 to the 5, depends on the situation. We do think of these numbers, this n equals 1, n equals 2, these tracks as being quantized. And quantized is just sort of a fancy way of saying that you're either on one energy level or you're on the other. So you're either on the first track or you're on the second track, like on rungs of a ladder. You're either on the first letter or you're on the second rung of the ladder. You're not in between. Okay, so it's impossible for an electron to exist in this range here, anywhere in between the two tracks. So when we're looking at hydrogen, what happens is we have one electron, and that one electron is on the n equals 1 track, lowest energy track, or lowest energy orbit. When that electron gets excited, because we plug it in with a lamp or we put it into a flame test, it's going to excite. It's got all this energy, so it's exciting to a higher orbital. It can move orbit, it can move away. And then at some point, that energy will move to the atom next to it, or the atom on the other side of the chamber, or whatever it is, and that electron will relax back down. Now, when that electron relaxes back down to its ground state, or its state closest to the nucleus, it has to release that energy. How does it release the energy? It releases it as light. So it gives off light. And that light is happening at those discrete lines on our spectrum. So when we look at hydrogen, when we excite the electron to just one level up and back down, when it relaxes down, it's only relaxing down one quote unquote floor, energy floor. So we don't have a lot of energy. So that's going to be the red light. All right. But what if that one electron jumps 2 floors? When it relaxes back down, it's going to produce a higher amount of energy. That's where we get the green. If that single electron instead got excited to the violet, or the highest level, and then relaxes back down, we get this violet light. So that electron is kind of moving up and down. When it comes down back towards its ground state, it's producing these increments of light. Why don't we get anything, in between here and here? Because the electron can't exist between this space and this space. It's either going to be here or it's going to be here. So that's why you get these discrete lines. So Bohr was able to, look at these spectrum, this observation, and work backwards and come up with this model of how electrons are organized. Awesome, right? That's so great. It's too simple of a model. It doesn't explain the spectrum past hydrogen. Okay, so it works for hydrogen, and then helium, lithium, beryllium, any other atom on the periodic chart, it doesn't work for. But we still use this model to explain electron distribution because it's so simple. We use it a lot of times in high school chemistry, but we're going to actually move out of the Bohr model, which, really, really simple. We've got these orbits, these little tracks, and we're going to move to the quantum mechanical model. So the quantum mechanical model of an atom was replaced by the Bohr model. It helped to explain hydrogen spectrum, but it's also been able to explain all the other elements on the periodic chart. In the quantum mechanical model, instead of having an orbit, we have what's called an orbital, so ends in AL. An orbital is different from an orbit, and that instead of it being like a track where we know exactly where the electron is rotating around the nucleus, now we have a probability map, or we have an area, a statistical area where we think the electron is. We don't actually know where the electron is. We can't know the location and the velocity of the electron at the same time. It's impossible. And if you're like, why is it impossible? Because that's like some high level physics stuff that I can't really explain. You have to go get a career in physics if you want to start getting an explanation for that. But for now, what we're going to say is that there's just a cloud, an area or a lobe where we think the electron is probably hanging out. The quantum mechanics totally revolutionized physics and chemistry, because in the quantum mechanical model, electrons don't behave in this sort of particle flying through space idea like we see on a macroscopic scale. Like you throw a baseball and I see the baseball coming towards me and I know how to catch it. That's not what's happening. Instead, there's no exact path. There's just like a field where the electron kind of comes in and out of existence in that area. And it can pop, here or there, wherever. So it's, again, probability cloud of where the electron is likely to be found. So this is more of what we would see on the Bohr model. The electron has a specific path and it follows that specific path and it's continuous. In the quantum mechanical model, however, the pitcher would have a harder time catching the ball because he only has a probability of where it's going to be. He doesn't know like exactly where the ball is going to land. There's a 40% probability it'll land here. There's 70% it'll be within his arm's distance. And there's also a, small percentage chance that baseball could end up on the other side of the universe. That's just how electrons are. They're weird. They do funky, weird things. So we're going to move away from the weirdness of it and just kind of do the basics with this, the logical basic part of it, which is to describe an orbital. So an orbital has two components. An orbit from the Bohr model just had one. You were either in the first energy or the second energy or the third energy shell. Now we have a number, which is known as the principal quantum number. That tells us what energy level we're at. So 1 is a lower energy than 2, 2 is a lower energy than 3. That's kind of similar to the Bohr model. But we, in addition, have a letter. And the letter specifies the principal shell of the orbital, or it explains the shape of the orbital. So now we're not just circled paths. We have kind of different shapes depending on what letter we get. So the first orbital that's out there is the 1s, 1 being the lowest energy and s being its shape. The shape of the s is a sphere. And we'll go through all the different shapes that we have. So the single electron in an undisturbed hydrogen atom, because remember hydrogen has 1 proton and 1 electron, that single electron will sit in the lowest energy orbital, which is the 1s. And that's the thing closest to the nucleus. This is called its ground state. So when you hear me say, hey, the ground state, it's all the electrons in their lowest energy position. There's only one ground state for every element. But if I was to say, I was to excite that electron could go to a variety of places, right? It could go to the 2s, it could go to the 3s, it could go to the 3p. It has a variety of places it can jump to. So all the atoms of each element will have only one ground state, but they have a lot of excited states because the electron has a lot of places it could go to, depending on how much energy it gets. All right, so energy increases with your principal number. So n equals 1 is the lowest energy. That's going to be the closest to the nucleus. N equals 2 is a little bit farther. N equals 3 even farther, and so on. The letters, which are known as our subshells, tell us the possible shapes for each of these orbitals. It also lets us know how many electrons we can put in that shape. So the S is a sphere, and it can hold a maximum of 2 electrons. So somewhere right, 2 electrons for the S. The p orbital makes what's called a dumbbell shape in 3-dimensional space. So there's an X dumbbell, a Y dumbbell, and a Z dumbbell. P's can hold 6 electrons, a maximum of 6. So if let's say I had 4 electrons, I could put 2 of them in the S, but then the other 2 have to pour over into the P because the S can't hold a maximum of 4. It can only hold a maximum of 2. The D orbital has very weird shapes. I don't expect you to know those, but you do need to know that the D orbital holds a maximum of 10 electrons. And then the F has, we're not even going to go into what those shapes are, but it is important to know that the F can hold 14 electrons. Okay, so S holds a max of 2, P holds a max of 6, D holds a maximum of 10, F holds a maximum of 14. Any of these shells can hold less than their maximum number if you don't have enough electrons to fill it up. So you can have a half-filled P. You could have like 5 in the P or 3 in the P or 1 in the P. So what's the difference between the 1s and the 2s? Both of them are spheres because they're S's. Both of them can hold 2 electrons. The 2 is just going to be farther away from the nucleus. So this is where you kind of want to envision, I'm going to skip forward here a little bit, envision like Russian nesting dolls, the smallest one being the one towards the center. So this 1s orbital sits closer to the nucleus, and this is the area that these two electrons can float around in. The 2s wraps around the 1s, okay? So it's a bigger sphere that's clipped around the 1s. The electron will sit somewhere within that sphere. As far as these spheres are concerned, they use, sometimes you'll see them represented as these dot density images, like this. So it'll be a sphere, or it'll have dot density where like the dots are more prominent, where there's a higher probability of the electron being. So we expect the electron to be somewhere around here. Lower density as you move out, because there's less likelihood that the electron is going to be that far from the nucleus. So you always fill the 1s first, and then you would go to fill the 2s when you're filling in your orbits or your electrons, because this is lower energy. So we pack in this to the lower onion layer, and then we work our way out. As far as the different types of shapes and the energies, the lowest energy shell, or the one that's closest to the nucleus, will only have the S shape. Or if you want to think of these as like floors on a building, this is a building that's sort of lopsided. So it's narrow at the bottom and it's wide at the top. So the first floor can only have this S shape to it. The second floor, though, has, because it's a little farther from the nucleus, it has more space. It can create the S shape, which is the sphere, and it also can create the P shape. As we move away from the nucleus, so now we're in the fourth floor, we have another option. We can make a D shape. And then as we get out to N equals 4, we can make an F shape. If we go to N equals 5, the fifth floor, there's only S, P, D, and F. We don't have anything outside of that. So when you're filling, you always fill the 1s first, and then you fill the 2s. And then after that, you fill the the 2p. Sometimes people say, well, don't we fill the 3s next? What about the 3d? What about the 5f? What do we do? Okay, so there's an ordering on how you fill them, and it is the same every time. And I'm going to show you how to fill that. Here is what the dumbbell looks like. So this is the p orbital, just FYI. So it kind of looks like a dumbbell and X, Y, and Z. This is the D. This is like, these are like balloon animals at this point. This is not, nobody made this up. This is just what the electrons naturally do, because electrons all have a negative charge. So they want to get as far away from each other as they possibly can. And these are the most efficient structures that the electrons can make and occupy and still stay away from each other. So how close, they want to get close to the nucleus, but they want to stay far away from each other. This is what happens. All right, so from orbits to orbitals. So the quantum mechanical model predicted the spectrum for hydrogen, and it predicted for all the other elements as well, which is great. We like that. The Bohr model was replaced with the more sophisticated model of the quantum mechanical or wave particle duality model. The Bohr model is still important, but we like the quantum mechanical model. So in the quantum mechanical model, we make these things called electron configurations. An electron configuration shows you, and this is, I feel like this is going to sound scarier than it is. And then once I show you the pattern, it's going to get easier. So stick with me. So it shows you where the electrons are laid out within a given material. So for hydrogen, for instance, hydrogen is number 1 on the periodic chart. So it has 1 electron. I'm going to put that electron in the lowest orbital. And the lowest orbital is going to be the 1s. Okay, so you will write 1s, and then you put the number of electrons that are within that orbital. So in this case, I'm going to put a little 1 here. Why don't I put a 2? Because there's not 2 electrons here. There's just 1 electron in hydrogen. Assume, as long as it isn't charged, that the protons and the electrons equal each other. So the electron configuration of hydrogen says, hey, we have 1 electron floating around that really small sphere around the nucleus. We can also represent this in what's called an orbital diagram. You make a box for your 1s. Each of these boxes can hold 2 electrons, and you put an arrow in it. Okay, so we put an arrow and we spin it up. It's important which direction the arrow is pointing. Specifically, when you add a second electron, you need it to spin in the opposite direction or point down. And I'll show you that in a little bit. So these are kind of a pain to do, just with the nature of like being online, you're not going to really have to be writing these, but you want to be able to identify them. So we've got orbital diagrams. Anytime you're doing in an orbital diagram, you always want the electrons to point in opposite directions like this. So you draw an arrow pointing down and then up, or you have an arrow pointing up and then down, doesn't matter. But they have opposite spins. This is because of a principle called Pauli's exclusion principle. It is important the electrons can't spin in the same direction. They need to spin in the opposite direction to create balance. So just make sure you're putting the arrows in the opposite direction. When you're doing your mastering chemistry and you've got the boxes, put the arrows in the opposite direction, or mastering chemistry is gonna freak out. So in multiple electron atoms, which is, I mean, everything past hydrogen has more than one electron. The subshells within a principal shell do not have the same energy because of electron-electron interactions. So different subshells within the same principal shell have different energies. This is where it gets a little weird. So the 4s subshell is actually lower energy than the 3d subshell, even though its principal quantum number is higher. So this has a lower energy or is easier to fill than this. I'm not going to stress about that too much. I'm just going to show you the filling order and like just either memorize it, or I'm going to show you how to read it off a periodic chart. So this is the ordering. You fill the 1s, then the 2s, then the 2p, then the 3s, then the 3p, then the 4s, then the 3d, then the 4p, then the 5s, then the 4d. And it's like, what's happening? I'm going to skip over this really quickly. Here's another way that it's written. Okay, this is the filling order every time. You don't put things in here until you've filled things in here, right? So we always start here, fill these, and go from there. They have it written like this. I hate this diagram. This does not work for me. So if you like this, you can follow this, but I always end up doing my arrow in the wrong direction and my ordering isn't right. So how do I come up with this? Well, you can memorize it, or let's look at the periodic chart. Jump forward. So in your periodic chart, we have a pattern that exists. The two columns on the left here are going to be known as the S block. So S block. And how many electrons does S hold? S can hold 2 electrons, right? And there's 2 columns. Okay, that's nifty. That's convenient. This helium, consider helium over here. Okay, so helium and hydrogen can kind of move back and forth. Over here, this column, these columns here, these 6 columns are known as the P block. How many does a P hold? A P orbital can hold 6 electrons. Okay, that's not a coincidence. That's part of the setup. In the middle here, we have the D block. D block. How many electrons does a D orbital hold? It holds 10 electrons. And how many columns do we have? 1 through 10. Then we have down here the lanthanides. This is known as the F block. How many electrons does F hold? 14, and there are 14 columns in here. So when deciding my ordering, let's say I want to get to oxygen. Okay, they have it written there, but I'm going to show you what we do. So look at these numbers. The number here is the energy number. So the first energy number or floor we hit is 1. And what block do we bump into? We bump into the S, right? So we're going to fill the 1s first. So let's fill the 1s. Do I fill it completely? Yes, we fill it completely until we get to the element we want. So I'm going to put a little 2 in the upper corner there because both of those slots get filled. So read this like a book, top to bottom, left to right, top to bottom. So we go across this, we've filled that. All right, what's the next place we hit into? We hit the second energy. So we're at the 2. And we bump into the P block. Or I'm sorry, the S block, right? So we're in the S block. So we have to fill the 2s next. Do we fill both of them? We do. So I'm going to put a little 2 in that upper corner. Now we're going to go across the expanse of our transitions and bump over here into the P block. We're still on the second floor, so we're in the 2P. I'm going to fill 2P. Do I fill my 2P fully? No, look at where oxygen is. It's not at the end of the P. There are 1, 2, 3, 4. So I'm going to put a 4 there because only 4 of the slots have been filled. Now, make a note here in the D that when you approach the D, D is always going to be 1 energy level less than the P and the S, or D equals N minus 1. Okay, so when we are filling, let's do bromine. All right, bromine's over here. We're going to start at the beginning. There's a pattern. It's the same thing. We start right here. We fill the 1s first. So the 1s gets filled first. Then I fill the 2s. Do I fill it fully? Yeah, because we're like nowhere near even close to getting to bromine. So we fill that fully. Then what do I fill? The 2p. So 2p. Do I fill that completely? Yeah. Okay, so we put a 6 there. What comes after the 2p? We're at the 3. And we bump into the S. So now I fill the 3s. Do I fill it fully? Yes. So I'm going to put a 2 there. After we get to this point, we jump across the void and we bump into the 3rd floor P. So we fill the 3p. Do we fill it completely? Totally. Go past argon. So 3p, 6. This is where it gets slightly tricky. We're on the 4th floor. We fill the S first. So we're going to fill 4s and we fill it completely. Now I need to fill the D. Okay, this is the first time I'm bumping into the D. The D is 1 floor less than the P or the S and the P. So instead of being at the 4D, we're going to be at the 3D. All right, that's just how it is. Same thing with this transition here. If you're filling the 5s, you then fill the 4D. The D is always 1 less than the S before it. When you get back to the P, you go back up to the floor level. Okay. So in this case, where were we? We were at the 4s, then we bumped into the 3D because the D is 1 less energy wise. Do we fill that completely? Oh yeah, we fill that completely. So I'm going to put a 10 there. Now we have come to the last section and bromine is there. So I'm going to fill the 4p. Do I fill it completely? No. 1, 2, 3, 4, 5. We put 5 electrons there. If we had made it all the way to krypton, he would be filled with 6. But because we went to bromine, we're at 5. You guys seeing how that pattern comes up over and over and how you can read it off the periodic chart? So I'm always going to fill in this ordering: the 1s, the 2s, the 2p, the 3s, the 3p, the 4s, the 3d, the 4p, the 5s, the 4d, the 5p, the 6s, the 5d. Then just FYI for you, the F is 1 less than the D. Okay, so it'd be 6s, 5d, 4f, but I'm not going to test you guys on the F block. Okay, so the biggest one you would have to make is barium. That'd be the biggest electron configuration that you guys would have to do. I won't have you do any of the latter ones. So we've got our S block, our 2 columns here, our P block, our 6 here, and our D block in the middle. No F block is down here, but you're not going to have to work that for a test. Any questions on that? We will do a couple of them. We'll practice a couple of them. I know it's like a little weird, but hopefully when you've done like 2 or 3 of them, you're going to see, oh, I'm filling it the exact same way. I always fill it. Okay, let's move back a little bit here. We skipped over some stuff. So helium is the second element on the periodic chart. It has 2 electrons, so we put a 2 in the S. Its orbital diagram would look like this: a box with 2 arrows spinning in the opposite direction. Lithium has 3 electrons, so we would fill the 1s. Right? We'd fill it completely, and then we'd put 1 electron in the 2s. It would look like this for its orbital diagram: arrow up, arrow down, and then a single arrow up. When we move into bigger things like carbon Carbon has electrons in the 1s, in the 2s, and also it has 2 electrons in the 2p. So this p can hold a total of 6 electrons. So when you draw its orbital diagram, make a rectangle that you can divide into 3 places. Okay. The D you divide it into 5, the F you divide it into 7. So this has 3 orbitals or quadrants that we can put the electrons in. Each orbital will hold 2 electrons for the total of 6. So when we're looking at the carbon, we're going to put our electron in here, and then an electron in here, and then here. When you're in the same orbital, you want to fill each box in individually first. This is known as Hund's rule, or that in the 2p, electrons will occupy the p orbitals with equal energy individually, and then you'll go back and double them up. Why do we do that? Because that makes a more balanced atom. Instead of putting, like if we didn't have this electron here, let's pretend that's not there. If we just put the 2 here, it's really lopsided. It's like sort of like the electrons are all clustered on one side of the atom, and that's not what's happening. The electrons don't particularly like each other because of their similar negative charge, so they want to spread out. So we'll always fill singularly, and then we'll go back and double up. That's true for the d orbital as well. You'll always fill singularly and then double up. Ugh, I hate that. I hate that. Okay, so let's look at some of the bigger ones. Nitrogens, oxygen, fluorine, and neon. Nitrogen has 7 electrons. Hopefully you're starting to see how these just sort of piggyback off the guy before it, right? Nitrogen here is very similar to carbon. It's just 1 additional electron. And if you look at your periodic chart, nitrogen comes right after carbon. So it piggybacks off of it. 1s2, 2s2, 2p, it has 3 instead of 2. So in that case, we put these in, and then we'd put these in singularly. When we get to oxygen, how is oxygen different than nitrogen outside of its protons and electrons, or protons and neutrons? Electron-wise, it has 1 additional electron. So now we've got 4. So we're going to double up, right? Then when we get to fluorine, we've got 5. So, oh gosh, we're almost full there, right? We're so close to being full. Look at neon. What's unique about neon? Look at every one of them is full and neat and balanced. That is a stable configuration. Okay, a stable electron configuration. All the noble gases do this. They form a complete outer shell. That means that the electrons have a partner, they're balanced, they don't want to be messed with. So usually the noble gases don't bond. Think about fluorine, okay, where it is located on the periodic chart. What charge did you put above the fluorine column, the fluorine, chlorine, bromine, iodine? Hopefully you have a -1 there, because fluorine predictably likes to eat 1 electron. Well, why would it eat 1 electron? Well, look what happens. If we add an electron to fluorine's configuration, what happens to the 5? It becomes a 6, and it looks something like this. The electron configuration now looks like a noble gas. So by fluorine eating 1 electron to become the ion, fluorine 1-, it now has a more stable electron configuration. What about oxygen? Oxygen's in column 6, but it likes to form a 2- charge, right? Oxygen, we put a 2- above that column. It likes to eat 2 electrons. So instead of having 4 electrons here, it becomes 6 electrons. Those 2 electrons get packed in there. It's like the noble gas. All these things tend to form ions to become what's known as isoelectric. Isoelectric meaning they have the same electron configuration as a noble gas. Everything wants to become like a noble gas, and this is why. If we go, let's do, I don't want to do one that's giant, but I do want to do one that's positive. Sorry, I can hear my daughter screaming and my brain is trying to like process multiple things at once. Okay. Let's go to the whiteboard. So if we do the electron configuration, well, actually, I'm going to have you do it. I want you to draw the electron configuration and the orbital diagram for sodium, Na. Not charged sodium, just regular sodium. Okay, so we assume equal protons and electrons. So I want you to write the electron configuration, and I also want you to do the orbital diagram, which are those like silly little box things. Okay, so I'm gonna kind of flip-flop between here and there. So sodium lies right here. Okay, so this is the place that I need to get to. So I need to fill the 1s first, and then the 2s, and then the 2p, and then some of the 3s. So your configuration hopefully looked something like this. 1s2, 2s2, 2p6, 3s1. Yeah? Thumbs up, thumbs down? Yeah, cool. Okay, awesome. So, you know, sodium is number what? Number 11? Yeah, number 11. So it should have protons should be 11, electrons should be 11. Sorry, I'm doing this like without a periodic chart. I'm trying to remember. Okay, so yeah, 11, 11. So these just, you know, these things should add up to equal 11. If they don't, you've done something wrong. Now, sodium tends to form this ion. So it's important when you're doing your electron configurations. Am I asking you to do the electron configuration of the element in stable or equal form, so equal protons, electrons, or am I asking you to do it as an ion? So sodium likes to form a plus charge, right? Na with a +1 charge. It's in column 1. That's consistently what it does. So looking at the electron configuration of this sodium atom, how is the ion going to be different? Well, if I'm a plus, what have I done? I've given away 1 electron. So this electron in the S goes away. So the electron configuration for sodium with a charge is going to be 1s2, 2s2, 2p6. So you do want to be able to make electron configurations for the ground state atom, but you also want to be able to do it for the charged ion. So you need to take into account the charge. Look at this. This configuration is similar or isoelectric to neon. If you're writing these electron configurations, oh, and then also I said to do the orbital diagram. So let's do the boxes. So 1s, 2s, 2p, 3s. Okay, so up, down, then I fill up, 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 and then I go back and fill down, 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 and then 1 here. This would be the orbital diagram. For the sodium plus, we would, with the positive charge, we would just cross this out, and this would be our orbital diagram. So, you know, this is true for all of them. If we go to our periodic chart, this one, but everything in column 1, it has 1 electron in that outermost shell. It wants to get rid of that electron to become like the noble gas before it, right? If sodium loses an electron, it becomes like neon in the isoelectric sense. Anything in column 2 likes to give up 2 electrons because it has 2 electrons in that outer shell. So something like calcium, for instance, if it gives up 2 electrons, goes backwards 2 spots to become like argon. Aluminum, we said, likes to give up 3 electrons. Aluminum will go through magnesium, sodium, and become isoelectric like neon. Same thing happens with the nonmetals here. They like to eat electrons to get to a noble gas configuration. So phosphorus likes to eat 3 electrons. 1, 2, 3 becomes like argon. Bromine, 1 electron. Krypton. So hopefully now those charges are making a little more sense. Like why everything in this column forms a 2- charge. Why would oxygen never form a 3-? Because it's never going to go to fluorine and then become like neon and then just blow past neon and become like sodium. Sorry, sodium. Sodium doesn't even want to be like sodium. Everything wants to get to this configuration. So if you're doing these electron configurations and you're like, these are total pain in the butt, is there a way to abbreviate them? There is, okay? So we had sodium down as 1s2, 2s2, 2p6, 3s1. What you can do is abbreviate with the noble gas that comes before it, not the noble gas that comes after it. So sodium, I take the part of it that is the noble gas before it, which is the configuration for neon. Gosh, my daughter is like really wailing right now. Can you hear her? Miles is like, yes, I can hear it. It's killing me. Okay, so we take this part here, the 1s2, 2s2, 2p6, and we just get to write neon instead. Isn't that nice? But you have to add whatever is left over. You can't just write neon because this isn't the charged sodium. It's the regular sodium. So we need to add that extra electron in there. So let's say we have something like barium. Barium is the biggest, actually, I want you to do it. Barium is the biggest element that you would be responsible for. So if you can do barium, then you'll be good to go. So you do barium. It's full form, not the diagram, just the electron configuration, the 1s2, 2s2. Do that for barium, and then I want you to do the abbreviation for it as well. So you can abbreviate with the noble gas before it, but do both of them. I'll give you just a minute and a half. Okay, so barium is number 56. Its location on the periodic chart, it's in that 6th column, or rather 6th row, 2nd column. So I got to go through quite a few things to get to it. I'll first fill the 1s completely, then the 2s completely. Then I bump into the 2p and I fill that completely. Then I fill the 3s completely, and the 3p completely. Once we get to the 3p, then we're in the 4th row. So we're right by potassium. I'm going to fill the 4s completely. And then I have to go to the D. Remember, the D is 1 floor less. So it's the 3D. And we fill that completely. That's just how it goes, okay? The 4, then it goes to the 3D, then it goes back up to 4p. All right, this is 1 lower than its buddies on the side. After the 4p, I'm gonna pop out right by rubidium, number 37, and that's the 5, the s. So 5s, and we fill that completely. Then we move into the D orbital. So remember, we have to go 1 floor down for D10. And then we go back up to the 5 and the P. We fill that completely. That's gotten us almost there. Now we're at the 6th one, right? So 6s2. Yeah, that's a pain to write. So what is the noble gas that comes before barium? Well, the noble gas before barium is it xenon? Xenon, yeah. So this whole thing right here could technically be substituted with Xe. And then I have to add the last little bits, 6s2. So anything that isn't included in the noble gas configuration gets tacked on the end. Any questions with that, with the filling order, with the abbreviation? If instead of barium, I happen to ask you to do barium with a 2+, that would mean you would take what its normal configuration is and you'd strip off those last 2 electrons, right? Which would, it would just end up being the xenon configuration. Our configuration is making a little bit more sense. And if you can make this happen, you can do any of the atoms before it and you'll be good. I think the trickiest part is right here and right here, just remembering that the D has to be 1 less than the 2 guys around it. So layering on top of the charges in their, like the positioning of them, in the periodic chart. So things are like +1 and +2. We also want to think about these things called valence electrons and core electrons. So valence electrons are going to be the electrons that are in the outermost shell. Okay, they're the electrons. Valence electrons are important. They're in the highest principal quantum number. They're the things that are going to be involved in bonding. Electrons that are not in the outermost shell, electrons that are in a lower energy number, those are called core electrons. So if I look at this electron configuration here for Si, silicon, its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p2. The valence electrons will be anything that's in the highest number, this and this. So the highest number we have is 3. How many electrons are there? 2 plus 2 for a total of 4 valence electrons. Okay, so silicon always consistently has 4 valence electrons. You can write it out like this, or you can just learn the trick that silicon is in the main group 4, column 4. Right, so we have column 1 and 2 on the left, and then 6 on the right for a total of 8. Silicon is in column 4, so it has 4 valence electrons. Oxygen is in column 6, it has 6 valence electrons. Hydrogen is in column 1, it has 1 valence electron. So that's a little easier than writing out the whole electron configuration. We're not going to spend a whole lot of time with valence electrons in this chapter, but next chapter, it's going to be essential that you can really quickly find the number of valence electrons. I wouldn't recommend doing this. I would just look at silicon, see that it's in column 4, and you can infer that it has 4 electrons, valence electrons rather. Let's look at something that's a little bit bigger. So selenium, hint, hint, wink, wink, selenium is in column 6. It has 6 valence electrons. That's how I would do it. But you could write out the electron configuration. Notice that the d orbital, like we said, that's 1 floor lower. So when we fill in the d orbital, we're actually filling in core electrons. We're packing electrons into a lower level. So we don't include those in the valence electron. We look at the highest number possible. In this case, it's 4. So we've got 2 here, and we've got 4 here for a total of 6 valence electrons. Again, selenium is in column 6, so it has 6 valence electrons. The noble gases that are in column 8 minus helium. Helium is okay with 2 electrons, and we'll get into that a little later. But neon, argon, krypton, xenon, and radon, they all have 8 valence electrons. They have a complete outer shell, 2 in the S and 6 in the P, which makes them particularly stable. So we've gone over all this. We know the S block, the P block, the D block. Right, there is one exception to the configuration in the transition metals. It's a little wonky. Oh, I got a question here. Grayson, the column number is always the number of valence electrons every time. Yes, for the main group elements. Okay, so for the 2 columns on the left and the 6 columns on the right, the number of valence electrons will correspond to the column you're in. So let's look at, everyone look at calcium. Calcium is in the 2nd column, so it will have 2 valence electrons. Aluminum is in the 3rd column, so it'll have 3 valence electrons. Phosphorus is in the 5th column, so it'll have 5 valence electrons. That information is layered on top of and is different than the charge. So, you know, phosphorus is in column 5. It has 5 valence electrons. It likes to eat 3 electrons, so it produces a -3 charge. So make sure you have valence electrons and charge mentally separated. Valence electrons is the number of electrons it has. Charge is how many electrons it predictably likes to eat or give up in order to become like a noble gas. Whenever you're looking at transition metals that are like these guys here or these guys here, when you have 4 in the D or 9 in the D, something happens. Let's look at chromium. So traditionally, from what you guys understand about configurations, this is what the chromium configuration would look like. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Okay, there's 4 electrons in that D. I'm going to draw the boxes just for these last 2. These are, they're all full. So, I don't think you need to see me draw those, but we've got our S here, specifically our 4s, and there are 2 electrons currently in there, and then the D, which would have 5 boxes. And this is 4, so we fill them in singularly, 1, 2, 3, 4. This is not the configuration of chromium. Why? Do you see how this is almost halfway full? Like if we just had 1 more electron, it would be halfway full. Well, d orbitals like to be halfway full or completely full. It's particularly stable. So anytime you have a 4 here or you land on a 9 here, an electron is going to go from this S position and it's going to move over here. So this is going to become 4s with 1 electron in it, and the 3d will have 5 electrons in it, 1 in each quadrant. So how does that change the electron configuration? Well, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s, just 1, 3d, 5. Because having 5 or 10 in that D is stable. Now, that only works when you're at 4 or 9. It's only when you really are going to steal 1 electron. If this was 3d3, we don't do that. Okay, it's just when it's 3d4 or d9. And you can see that on this chart over here. I'll give you a second to write down whatever you write now. Okay, so let's go to this configuration here. You see how here we've got 4s, like we've got our 4s filled in all these with 2, 2, 2, 2, 2, and then here, bam, we go to 1. What's happening in the chromium is that this electron is moving here to give this 5. Same thing here, we've got 1. It's moving this to get 5. Over here, we can see that it's happening as well. So we're stealing the electron from the S and we're putting it into the D to get this to be 10. Right? Normally this would be 2, or we would think it would be 2 and 9, but it moves over. This happens in other places too. So like, platinum here, one of the electrons goes from the S and bumps it into here to get this to be 9. This is why transition metals have more unpredictable charges. Okay, I don't really expect you guys to know some of the ones in here, but like chromium here and copper here are really the 2 exceptions that I want you to know. So 2 exceptions, chromium, we bump the electron up. Copper, we also bump the electron up because a half-filled D and a completely filled D are stable. Okay, we already talked about this. We talked about this, why these things form predictable charges, right? Everything wants to be like a noble gas. So it likes to have 2 in the S and 6 in the P if the P is available. On the first floor, we don't have a P, we just have an S. So that's why this is okay with 2 electrons. But all these things want to become like a noble gas. So sodium, lithium, sodium, potassium, rubidium, cesium, and francium, they all have 1 in their outermost shell. Let's just get rid of that 1. And now we become like a noble gas. So that's why you've consistently put a +1 above column 1. Same thing with column 2, we put a +2 because it ditches its last 2 electrons to get it to be like a noble gas. And then if we go to the other side of the periodic chart, this is the electron configuration for each of these. They all have 2 in the S and 5 in their outermost P. They're so close to being complete. If each scenario, if they just eat 1 electron, what happens? They move into the configuration of the noble gas in front of them. So that's why these guys like to form a 1- ion to get to the noble gas configuration. Again, yeah, they have predictable charges. These guys can do funkier things with their electrons. That's why they tend to transition. The transition metals tend to have varying charges. So the last little thing that we're going to talk about here are trends that we find on the periodic chart. Divide your periodic chart into the lower left-hand corner and the upper right-hand corner. Size, the lower left-hand corner is the biggest. The upper right-hand corner is the smallest. So if you want to write down here, large, and up here, small, and they're just sort of all relative to each other. They don't include Francium here, but sometimes people call that one Fat Frankie. Remember, he's the biggest guy. Okay. Atoms get bigger as you move down because you're increasing the size of your Russian doll, or you're increasing the onion layers, right? Here we only have the first floor. Here we have the second floor. Here we have the third floor. Here we've got a building that's like 6 layers deep. So these guys get bigger as you move down. This one makes a little less sense intuitively. As we move across the periodic chart, we don't get bigger, we actually get smaller. And you may be thinking, well, aren't we adding electrons? Shouldn't we be getting bigger? Aren't we adding like volume? Well, we're adding electrons, but the electrons are being added on the same floor, right? We're on the second floor here. So we're just sort of adding more people to the second floor. Doesn't make the building taller if more people are on the second floor. But what are we also adding as we move across? We are adding protons, and protons pull the electrons in closer to them. So as we move across, we're adding more electrons to the same floor, but that floor is actually going to creep closer to the nucleus because of the protons pull. So that is why we get smaller as we move to the right. So you'll want to be able to have, a general understanding. I could give you like a series of 5 atoms and say which one is the biggest, or rank them biggest to smallest or something like that. The other property you need to know is ionization energy. Ionization energy, it doesn't even tell us what ionization energy is in the slides, but ionization energy is the amount of energy it takes to remove an electron. So how easy is it to steal an electron? Well, ionization energy is going to be highest in this upper right-hand corner, and it's going to be lowest in this lower left-hand corner. So fluorine is really hard to take an electron from. Why? Because it wants to eat an electron. It doesn't want to give up an electron. It wants to eat one to become like a noble gas. Whereas over here, Frankie, he's huge. His outer electrons are like pretty much falling off. They're so far away from the nucleus. And he wants to become like the noble gas in front, behind him. So he wants to become like radon. So he's like willing to give an electron up anyway. So super easy to pull the electrons off here. Much more difficult to get them here. They're smaller. The electrons are closer to the nucleus, and they want electrons to get to be a noble gas. The last one, you guys should already kind of know this idea, but metallic character. So the lower left-hand corner, where Frankie is, he's the most quote unquote metallic-like thing on the periodic chart. He has the most metal-like properties. The least metallic thing is going to be the upper right-hand corner, where we have helium, fluorine. As you move towards the zigzag line in your nonmetals, you become more metallic-like, right? So here's our, these are nonmetals, these are metalloids, and then these are metals. And cesium is much more metallic than copper is, or rather cobalt. And cobalt is more metallic than copper. If we were to compare nonmetals, sulfur, obviously sulfur is not a metal, but sulfur has somewhat more metal-like properties than, say, fluorine, because it's closer to the zigzag line. Okay, so lower left-hand corner, large, metallic, low ionization energy, or easy to take an electron. Upper right-hand corner, small, high ionization energy, hard to get an electron, and what is it? Non-metallic. So know those corners, and then they just kind of shuffle in from there. And that is it for chapter 9.